So here we are, section 12.1, looking at rates of change. We did this in our previous topic. This yellow box you would have seen in the past. But let's look at our two examples of rates of change. We have an average rate of change, and here you can see the average rate of change between the points P and Q. We just draw a secant line and we calculate the gradient of that secant line. So we're looking at the rise over the run. So this will end up being some type of quantity with a unit of measurement of meters per second. So it's simply rise on run, and that's how we calculate it. And here on the right hand side we have the instantaneous rate of change at this particular point P. So we know that we can, in the graphical approach, we can just apply a tangent line and then calculate the gradient of the tangent line, and the gradient of that tangent line will be exactly equal to the gradient of the curve at that point P. But of course now we've started using calculus, so what we can do is calculate the derivative of this equation and then substitute the x value into that derivative to get the gradient at that point P. Problem 1. Given that f of x is equal to this quadratic, work out the average rate of change between x equaling 2 and x equaling 4. So for A, we've got average rate of change. We simply want to substitute. The top line here will represent the rise, the bottom line will represent the run. So we want f of 4, and that will give us the y value for where x is equal to 4, minus f of 2, that will represent the y value for where x equals 2, over 4 minus 2. And you can see the calculations here, and we end up with an average rate of change of 4. B, determine a new function that describes the rate of change for any point x. So here we're talking about the derivative. So for B, we've got f of x equaling the quadratic, and then we want to work out its derivative. So f prime of x equals 2x take 2. So we can now work out the steepness of this curve for any value of x by simply substituting the value of x into this derivative here. And for C, we need to work out the instantaneous rate of change when x is equal to 4. So obviously we're going to be involving the derivative function. Whenever we hear instantaneous rate of change, you're talking about a tangent line or the derivative function. So the instantaneous rate of change is simply going to be the derivative. So here's our derivative, and now substitute x equaling 4 into that derivative and we'll get 6. So the steepness of the curve at x equaling 4 is 6. D, do parts A, B and C using CAS. So to begin with, and we've gone over this a lot, but what you need to do firstly is define f of x. Then your average rate of change is going to be the fraction f of 4 minus f of 2 over 4 minus 2, and we'll spit out 4. Notice that what my answer here in red, that's all you need to show. Okay? Stuff in green, remember, that's just the steps that you do on your CAS. The second part, we need to work out the instantaneous rate of change. Okay? We'll come up with the derivative function. So f of x equals this, f prime of x equals that, and that's all I need to show. How did I do it? Menu, calculus derivative, and that will bring up the d of something dx, put in f of x here, and remember that's defined. And finally, work out the rate of change for where x is equal to 4. So in red I'll write f prime of 4 equaling 6. How do I work it out? Menu, calculus derivative. I'm working out the derivative of f of x, given that x is equal to 4. So that's what I need to put into my calculator to produce the 6. So just remember that with your CAS calculator, the first thing the CAS will do is work out the derivative function of this, and then it will substitute x equaling 4. So here we've got problem 2. It's just basically about a nuclear bomb going off, which sounds a little bit dangerous, obviously. We've got this nuclear blast, and it spreads out from ground level in a circular manner, so that's really important to note. A, write down a relationship between the area of the ground in a kilometres squared, over which the shock wave passes and its radius are kilometres. So it's very simple. The area equals pi r squared, just the formula for the area of a circle. B, find the rate of change of A with respect to R. So whenever we're talking about rate of change, we're thinking about the derivative. So dA dr, change in area over change in radius, is equal to 2 pi r. So we just take this rule here and work out its derivative. C, find the rate of change when the radius is 2 kilometres. So we make use of our derivative and we substitute r equaling 2 into it. And we end up with 4 pi kilometres squared per kilometre. So the area is increasing at a rate of 4 kilometres squared for every 1 kilometre of radius increase. That's approximately equal to 12.56 kilometres squared per kilometre. Remembering that our rate, the unit of measurement we're talking about for our particular situation here, is that it's change in area over change in radius. The area is in kilometres squared and the radius is just in kilometres. D, what is the rate of change of A when the area covered is exactly 214 kilometres squared? So we start off with our area rule. We make the area equal to 214 and we solve for R. This is approximately equal to 8.25 kilometres. Now we're not after what the radius is. For this question, we're after what the rate is. So what we need to do now is substitute that found R value into the derivative. So we're using the derivative rule. We substitute R equaling 8.25 and we get 51.86 kilometres squared per kilometre. So what we've just discovered here is that when the circle is exactly 214 kilometres squared, that will mean that the radius is 8.25 kilometres, and that means that the rate in which the area of the circle is increasing is 51.86 kilometres squared per 1 kilometre increase of the radius. Problem 3, it's a fairly straightforward type of question. We've got y equaling 3x squared, take 5x plus 10. We need to find the rate of change of y with respect to x. So whenever you see those kind of words, you know you're talking about the derivative. And we want to work out that derivative for where x is equal to 2a. This would be really straightforward if this was something like x equaling 5, because we know what we'd have to do here is work out the derivative function and then just substitute x equaling 5 into it, and that will spit out a number which represents the rate of change. But the only difference here is that we've got x equaling 2a, this unknown a amount. Our process is just the same. So we have our y rule, we work out the derivative, and now we substitute x equaling 2a into the derivative, and then that gives us an expression in terms of a. So 12a take 5. That's our answer. It's all about a pool. Basically, we have the volume of the pool given by this rule here, where V is in litres and T is in minutes. Notice that the domain is between 0 and 48. It's a fairly straightforward kind of volume rule. Notice it's in the format of being a quadratic in turning point form. Okay, so usually with our quadratic, we'd have the variable here, then plus a constant, but the constant's listed first. Not a major deal. Whenever we get one of these kind of equations and we're allowed to use our CAS, the first thing we should do is define the function. So in my CAS, menu, actions, and define. And I'm not going to use the t variable, I'm going to use x because that will enable me to graph it. So v of x equals 5,000 plus 15 times the bracket 48 minus the variable x I'm using, and that's to the power of 2. And I've got a condition here for my domain. We know that our domain is between 0 and 48 minutes, including those values. So I'm going to use my given that symbol. and it's between 0 and 48. So now it's defined, and that's going to make things a lot quicker for me. Back over to our problem. How much water is initially in the pool? So whenever we hear initially, that's at the beginning. So you can see there that our time is 0 at the start. So I'm simply working out V of 0. And you can see it's 39,560 litres. The way that I write that, initially time equals 0, so V of 0 equals 39,560 litres, nothing more. B, what is the minimum amount of water in the pool? Now, I've worked out this answer by simply recognising that my equation is in turning point form. So if I look at the equation, then my turning point is going to be what makes the bracket equal to 0 here, and that's where t equals 48. And so that's fine, that's t equaling 48. And then this part here tells me the value for y, or in this case the volume. So I'm looking at 48, 5,000 as my turning point. Notice also that the coefficient here is a positive, so therefore it's going to be an upright parabola. And that's what I've written down in green here. I don't need to write that down in my solution. It's simply 5,000, and that's the litres. How long does it take for the pool to be drained to its minimum level? So we just worked out that the minimum level is 5,000 litres. So you can see what I've done here is V of t, make it equal to 5,000, and I want to solve for t. And I end up with 48 minutes. We also knew that from above anyhow, because we knew that there was a turning point at 48, 5,000. Just to show you on the CAS what we'd do, be menu, algebra, and solve. And we want that function v of x to equal 5,000. And we're solving for x. You can see it produces 48 minutes, which is not a big surprise. Part D. What is the average flow rate out of the pool between 5 and 15 minutes? So here we're not talking about instantaneous rate of change, we're talking about the average rate between t equaling 5 and t equaling 15. So average flow is going to be V of 15 minus V of 5 over 15 take away 5. So that there just put into your CAS, and remember V of t is already defined, and that produces negative 1,140 litres per minute. So that represents how many litres we are losing every minute that goes by. That's the average loss of water between the 5 and 15 minute marks. E, what is the instantaneous rate of change at 15 minutes? So for E, V of t function, you then work out its derivative, and you substitute t equaling 15 into the derivative to produce minus 990 litres per minute. How do we do that on the CAS? So it's simply menu, calculus, derivative. We're doing it with respect to x, remember, not t, and we want v of x. And given that, x is equal to 15. And we produce that negative 990. Remember what the CAS has done here. It's firstly taken the v of x function that has been defined, it works out its derivative, and then it substitutes x equaling 15 into it. So that's our info. And also, just to show you the graph for f, here's our graph. Remember that the domain is between 0 and 48, including those values. That's why we have solid dots at the end. That's going to be a turning point, so it's not a surprise that we get this shape taking place, that subtle curve. We can go home screen and then we'll create ourselves a graph, and we want v of x. And of course, when I sketch this, it's not going to be over the appropriate domain, but if I change things to my window settings, and I might go for negative 10 minutes, I'll go up to 50 minutes, I'll go negative 10,000, and I'll go up to 60,000. That should show me everything I need. Alright, and you can see there's that graph joined and shown for you, similar to what I've just sketched here. So that's the pool question.